If I'm really careful about power supply voltage and biasing, I can drive a full watt out of these small signal transistors into a dummy load. Hi, I'm Kevin. Welcome to my cave. Last time, we got started on a journey toward designing a BJT-based power amp. For the final stage, we settled on a push-pull configuration of transistors operating in class AB, each transistor conducting for a little over half the power cycle. The circuit we demonstrated needed to drive a high resistance. We used 60 ohms, and produced only a piddling amount of power. We were able to give that 60 ohm load a sine wave of 12 volts peak to peak, which is just 4.24 volts RMS. That's a power of just 300 milliwatts. Let's try to improve that. With these small signal transistors, how much power could we actually put into a small speaker? Could I triple that power, or more, and deliver it to an 8 ohm load? I should warn you, this looks to be another long video. I'm planning to go through my reasoning for every single component. I don't want to just hand you a cookbook, much less a finished design. At the end of the series, I do plan to give you a summary of how to design an amp of this type using your own requirements and components. So let's get started. Let's review what we have so far. We're driving some known load impedance. Our circuit has an output stage with a pair of emitter followers wired in a push-pull configuration. We saw last time how we need ballast resistors on the emitters to stabilize the circuit against thermal runaway. We had an op-amp driving our circuit, and the op-amp output was driving a stack of resistors and transistors. The idea was that when there's no input voltage, the base of transistor Q1 will be a little bit more than a diode drop above ground, so Q1 will pass a little bit of quiescent current. And similarly, the base of Q2 will be a little bit below ground, and Q2 will pass the same quiescent current. We chose component values to deliver a few milliwatts into a 60 ohm load. The whole amplifier was enclosed in a feedback loop to correct any nonlinearities in the followers. We found that the op-amp needed additional compensation to keep the amplifier from oscillating. Now I'd like to see if I can adjust component values for more power. Can I derive a watt of average power into an 8 ohm load using generic small signal transistors in this circuit? Please indulge me for a brief interruption. As longtime viewers of this channel know, it's always free to all comers. Nothing is ever paywalled. But I do make one request of my viewers, that you take care of one another. To that end, all my ad revenue goes to charity. The current featured charity is World Central Kitchen. It has a sole mission: bring freshly prepared meals to those living in the wake of a natural disaster, a man-made emergency, or a humanitarian crisis. It is a team of food first responders, mobilizing swiftly to get meals to the people who need them most. Its model of swift action in time of need, leveraging local resources and adapting in real time, reflects a belief that a nourishing meal in a crisis is much more than a plate of food. It's hope, it's dignity, and it's a sign that someone cares. At the time of filming, World Central Kitchen has served over 600 million meals in communities all over the world. I know that Kevin's Cave people are a generous lot who believe in taking care of others. Won't you help out today, using the link up here or down there or at any rate somewhere nearby? Thanks so much for your generosity. And now back to the video. With any power amplifier, it's easiest to start the design from the output and work our way back to the input. In the output stage, there's only one current to concern ourselves with. The quiescent current is small enough that there will be only a few % error in the output power if we just ignore it and assume that only one output transistor is conducting at a time. Given that we're pushing 1 watt into an 8 ohm load, we can easily derive the RMS output current, 354 milliamps. We'll also want the RMS output voltage, 2.83 volts. It's usual to quote the output power assuming that the output signal is a sine wave, So the peak output voltage and current are their RMS counterparts times the square root of 2. Finally, we need a name for the voltage at Q1's emitter because it enters into several calculations. We need to get a value for the resistors R1 and R2. Typically, they will be somewhere between a few tenths of an ohm and a few ohms. A rule of thumb that I like to use is to have each one drop a diode drop at the intended peak output current. If I apply that rule here, I get a nice standard value of 1.2 ohms. The next thing we need to do is to work through the power budget for the two output transistors. The first question to answer is whether the transistors can handle the peak output current. In this case, half an ampere. A glance at the datasheet shows that we're safe. The continuous current rating is higher than the surge current we're putting in for brief peaks. The datasheet for the PNP transistor has the same figure. Now we need to look at the power dissipation. Can the transistors take the heat? We find the instantaneous power by getting the collector to emitter voltage from Kirchhoff's voltage law and multiplying by the collector current. I like expanding the result out as a polynomial in the current I. To me, that form makes intuitive sense. The two terms are the total power coming from the supply, and a combined term that's the power dissipated in the ballast resistor and the power delivered to the load. The difference between the two terms is the power dissipated in the output transistor. That formula tells us immediately that we want to choose as low a power supply voltage as we can, while still delivering the desired power to the load. A higher voltage is just going to heat the transistors. How low a voltage can we get away with here? Well, let's look at what happens at peak output current. We get the voltage across the load from Ohm's law. In the same way, we get the voltage across the ballast resistor. The base emitter voltage of the output transistor is, of course, a diode drop. But we have to be careful here. The datasheet warns us that with half an amp in the transistor, that diode drop could be as much as 1.2 volts. We need to make sure we're taking that into account. Adding up those three voltages gives us the base voltage on the output transistor. For the bias servo to supply that base voltage, the power supply has to be a higher voltage still. If I supply the values of the output current and the two resistances, it looks as if a power supply of plus or minus 6 volts should be enough. I'll run with that. Now that we know the collector voltage, we can start analyzing the power dissipated in the output transistor. Let's recall the equation that we had for instantaneous power dissipation. It's interesting to note that the dissipated power is not at its maximum when the maximum power is delivered to the load. Instead, the power curve is a parabola, with the maximum somewhere in the middle of the range. If you remember from high school algebra the formula for a vertex of a parabola, you can calculate just where that maximum falls. If instead, like me, you forgot that formula as soon as you learned calculus, differentiate the dissipated power with respect to the current and set the derivative to 0. In either case, we can also get a formula for the maximum power. For our component values, the peak power is just under a watt. 1 watt is above the rated power of the transistor. That power level might be alarming, but the average power will be at most half of the peak because the transistor is conducting for only half the cycle. It will actually be substantially less than half because the rest of the power curve is below the peak. Let's find the average power. Over there in the front row, will you tidy up the chalkboard for me? Thanks. As the great mathematician Ernst Snapper once told me in a lecture, I'm not asking you to clean the board because I'm too tired to do it. I'm asking you because I'm too lazy to do it. I wouldn't want you getting the wrong impression. We have our function for power dissipated in the transistor as a function of the load current. And we're assuming that the output voltage is a sine wave, so the load current is also a sine wave. I'm taking time out of the equation, by the way, and putting everything in terms of the phase angle theta. We can substitute that sine function for the load current in the top equation. The current on the positive half wave determines the instantaneous power in the transistor. And that defines the instantaneous power dissipated in the transistor as a function of time, or rather of the phase angle. It's a peculiar two-humped waveform. In the region where the output current is highest, the dissipated power in the transistor actually decreases. Not realizing this gotcha has led designers astray. To get the average power, we need to get the area under the curve for 1/2 cycle, and then divide by 2 pi, the length of a full cycle. It's a full cycle, not a half cycle, because the transistor is dissipating no power in the other half. We can write the integral for that area under the curve. I'm going to fly through the calculus here, so feel free to pause the video and work through it. Be sure to let me know in the comments where I messed it up. We integrate the two terms separately, yielding rather a mess. But when we grind through the algebra, a bunch of things cancel out, and we're left with a formula for power dissipated versus the maximum output current. But now we see another issue. There's still an I² term in our equation. We have another parabola here. Not only does the peak power dissipation come at a current that's less than the peak, but the average power dissipation in the transistor is maximized when the average power to the load is less than the maximum. We can do the drill of finding the vertex of the parabola once more, which finally gives us a formula for the worst-case continuous power dissipation in the transistor. If we want to, we can get the peak output current at which that dissipation occurs, and from that, of course, we can get the RMS voltage and average output power that trigger the worst behavior. In any case, if we assume a resistive load, then this is the power dissipation we have to design for. Fortunately for us, when we run our component values into the formula, we're still well within the 625 milliwatt power limit of the transistor. Now that we've shown the output stage can drive the load, we can fill in the resistor values in the bias servo. First, let's choose a quiescent current for the output stage. 5% of the peak output current is usually a pretty good trade-off between efficiency and linearity, so we'll go with 25 milliamps. What voltage drop will that current induce across the emitter-ballast resistors? Looks like 30 millivolts. The bases of the output transistors will be a diode drop above and below that voltage. And of course the collectors of the servo transistors are a diode drop away from the input, which is at ground in the quiescent state. We also have to choose a quiescent current for the bias servo. I'll choose 5 milliamps, somewhat arbitrarily. R4 and R5 each have to drop 30 millivolts. Ohm's law gives their values. 6.2 ohms is the nearest standard 5% value. R3 and R6 have to drop the difference between the supply voltage and the base voltage of the output stage. 1.1 K is the nearest standard value. Now all our resistor values are filled in. Let's run this circuit in a simulation to make sure I didn't mess something up. It's a good thing I decided to simulate it. I've made a mistake. The circuit isn't working the way I wanted. The output is clipping horribly at about 2.1 volts. It is working properly if I change the input voltage to 2 volts. But something's obviously going very wrong beyond that voltage. When we look at what's happening when the simulation shows the circuit clipping, the problem becomes pretty obvious. On the positive half cycle, the bottom output transistor is cut off, so we can ignore it and its circuitry. And when we're clipping, we saw in the simulation that the upper transistor of the bias servo is cut off as well. The op-amp is putting out a higher voltage than we're seeing on the output transistor's base. That means we can ignore most of the amplifier and look at just the handful of components that are delivering current to the output. Let's see what the transistor's base current is. If you recall our view of the emitter follower as an impedance transformer, we can look at the base circuit as being a diode drop plus the emitter resistance multiplied by the transistor's beta. We'll optimistically assume the beta is 100, so the base resistance will be 920 ohms. The simulation shows the base to emitter drop as 740 millivolts at the relatively high current that the transistor is passing. That's enough information to calculate the base current. It's about 2.6 milliamps. Now we can go back to looking at the transistor's output. The collector current of the transistor is approximately beta times the base current. Since we've optimistically assumed 100 for the transistor beta, we get a figure of 260 milliamps for the load current. That's only about half of what we need. I need to change this design. My first inclination was to take the caveman approach of pounding on it with a bigger rock. Use as much smaller pull-up resistor in the bias servo, and scale the resistor that sets the quiescent current to match. And, well, it works in simulation. The clipping is no longer there. The circuit output looks clean. But that pull-up resistor is dissipating about 0.8 of a watt at its peak, or 300 milliwatts average, and there's a pull-down resistor that's dissipating the same power. And the op-amp is being asked to put out nearly 80 milliamps, certainly more than a cheap op-amp will provide. We'd have to build a power amp to drive the power amp. All that power dissipation has destroyed our goal of making an efficient amplifier. Let's try something else. My second thought was to remove the output transistors and replace them with Darlington pairs. That's a perfectly reasonable idea, and there are a lot of commercial amps that work that way, but it's not my favorite approach. If we look at the voltages at peak output current, we will see the same stack up as before, except that we now have to add 2 diode drops instead of 1. The second diode drop will have to be accounted for in the collector voltage. 6 volts won't do it anymore. Then when we're computing the average power dissipation, it will also be higher because of the term that depends on the collector voltage. The amplifier will be less efficient and its power output will be lower because the power output is limited by the power dissipation in the output transistor. But what I find more significant is that we're going to have to design the bias servo to have the double diode drop. It's going to be tricky to match it to the Darlington transistors. One of the two will be running hot and at high current. The diode drop and the beta are going to drift with temperature. The other transistor will stay nice and cool because the current in it is much lower. By contrast, the reference transistors will be running much more sedately and much cooler. The differences may give rise to unwanted behavior, like an op-amp that shows bad crossover distortion, but only until it warms up. Designers have a bunch of interesting tricks to deal with these problems, such as mounting the reference transistors on the same heatsink as the power transistors. But we've already used a better approach in several earlier videos. Instead of using Darlington pairs, let's put in Sziklai pairs instead. With a Sziklai pair, there's still only 1 diode drop from collector to emitter at peak current, and the driver transistor doesn't pass much current itself, so it stays cool. Only the output transistor heats up, and its diode drop doesn't control the output current. One major function of the resistors in the Sziklai pairs is to stabilize the base to emitter voltage of the driver transistor. We'll do that by stabilizing its collector current. The Ebers-Moll transistor model gives us the equation for the collector current. If we take the logarithm of both sides, we can rearrange the terms to give us the base to emitter voltage when we know the collector current. If resistor R8 weren't there, the driver transistor's collector current would be the output transistor's base current. That base current would vary from a few nanoamps of leakage current when the output transistor is cut off, on up to the peak load current divided by the output transistor's beta. That beta might be as low as 40 when the output transistor is heavily loaded, So with our peak load current of half an amp, we're likely to need 12.5 milliamps of base current. What will the impact of that change be on the driver transistor's base-to-emitter voltage? Well, we can use the formula that we have for the base-emitter voltage, subtracting the voltage at the low end from the voltage at the high end. When we simplify this equation, the saturation currents cancel out. We're left with the thermal voltage times the log of the ratio of the currents. With the thermal voltage of 26 millivolts at room temperature, we predict a difference of over 1/3 of a volt, so we need that resistor for stability. I'd like the difference to be less than 10% of a nominal 600 millivolt diode drop. Now let's see what happens if we make resistor R8 carry a current that's just 1/4 of the peak base current of the output transistor. We know the voltage drop across R8 will be a diode drop, so we can calculate the resistance we need. We'll round that down to a standard value. A little extra current doesn't hurt. In fact, the smaller R8 is, the more stable the base-to-emitter voltage will be. Now, during the time that the output transistor is conducting at all, the minimum collector current in the driver transistor will be 25% of the output transistor's max base current, and the maximum collector current will be 125% of the output transistor's base current. The ratio between these two values will be 5:1. Thermal voltage times the log ratio gives a spread of 42 millivolts. Lots better than the 1/3 of a volt that we got before. Now, once again, we need to come up with the resistor values in the bias network. Let's review the procedure. R3 and R6 both need to supply enough base current to the Sziklai pairs. We know Q1B's collector current. It's Q1A's base current, plus the current that Q1A's base emitter drop will pull from R8. When we plug in our current set of values, we get a figure of a little under 17 milliamps. Q1B's base current will have to be its collector current divided by its beta. With that small a collector current, we can assume a beta of at least 100. The base current will be a tiny 167 microamps. R3 has to be small enough to drive that much current with a diode drop across it. I'll use 600 millivolts for the diode drop, given the tiny base current. The calculation says exactly 3.6 K. I want to make sure there's enough current, so I'll pick 3.3 K instead. Now on to R4 and R5. If you recall, they're added to regulate the quiescent current through R1 and R2. That is, the current that will flow when there's no voltage at the circuit input. We already chose what that current should be, and it determines the voltage across each ballast resistor. We need the voltage at the base of Q1B to be a diode drop above that. We get there by having Q3 provide the diode drop, and then we need R4 to set the quiescent voltage. R3 will drop the remaining voltage from the supply. 5.37 volts. Ohm's law will give us the current through it. 1.5 milliamps or so. We can ignore the minuscule current into Q1's base, so Ohm's law will then tell us the resistance that R1 needs to have. For the values we're working with, that's a little over 20 ohms. I'll use 22. It's better to have too much quiescent current than too little. Too much only costs a small amount of efficiency. Too little brings the crossover distortion back. Now that we have all the component values, we can take this design back to the simulator. It's looking almost perfect. The circuit output matches the input. The op-amp is running at a nice leisurely peak current of 3 milliamps. The power dissipation of the servo transistor, the two pull-up resistors, the driver transistor, the output transistor, and the ballast resistor, all look as if nothing is going to let out the magic smoke. We've just got one remaining little problem. If I cut the input voltage to 0, the quiescent current is all wrong. It's only about 10 milliamps. This is coming from a mismatch between the base emitter voltages of the servo and driver transistors. Which is unsurprising. They run at different currents, they see different temperatures, and in an actual build they may not even be the same transistor type. Predicting the quiescent current correctly turns out to be a problem in almost all amps of this type. In addition to the difference in temperature and current, there's always manufacturing variation in the transistors. It's really hard to compensate for everything in the design, so designers of this sort of amp have mostly resorted to using a trim pot so that the quiescent current can be set as part of assembly and test. The circuit we're using would require 2 trimming steps to set the 2 quiescent voltages. So let's get rid of this part in the middle and replace it with a circuit that can adjust the current with a single control. The way this circuit works is straightforward. If you remember from the second lesson of this course, the Q3 will adjust its base collector resistance to keep its base emitter voltage at a diode drop. But the resistor between base and emitter is part of a voltage divider, and we can ignore the tiny base current. The resistance of the top leg will vary from 6.8K to 16.8K. That will mean that the voltage dropped across R4 and RV1 will range from 0.68 to 1.68 times the voltage across R5, depending on RV1's setting. The voltage drop across the entire regulator will be between 1.68 to 2.68 times the base emitter drop of Q3. Surely the 2 diode drops plus the quiescent voltage that we need is in that range somewhere, and we can tweak RV1 to find the setting that gives us the correct quiescent current. This is what you might learn in a class on the subject, and it's what I designed and wrote down in my notebook. But it was bedtime, and I went to sleep before making this segment. When I woke up, I realized my mistake. If you deploy a power amp design like this, you may well find that you have units failing when being trimmed. The culprit is the potentiometer. Did you ever hear a circuit crackle when you turned a pot? That's a really common failure mode with potentiometers. What's happening when you hear that is that the wiper of the pot momentarily loses contact with the surface it's riding on. It's as if for a brief instant the wiper wasn't there. Even when you don't hear a crackle, it might be that contact was lost for too short a time for you to hear. What that will do in this circuit is to send a sudden burst of current through the output transistors. And that burst may be enough to take them out of their safe operating area into second breakdown, since the high current is being paired with a high voltage drop. That's instant death for a transistor. The fix is simple. Put the potentiometer in the bottom leg of the voltage divider. Now if the wiper loses contact, the voltage drop from collector to emitter of Q3 takes on its minimum value. That's going to be less than 2 diode drops, so it will have the effect of turning off the quiescent current altogether, which is safe for all the transistors. We'll have the trim procedure start with turning the pot all the way to the bottom before applying power, and then raising it until the voltage across R1 and R2 reaches the correct value. Don't ask me where I learned this little tidbit. Oh, and we're going to need now to connect the op-amp to one end of this servo circuit rather than the middle. That's perfectly fine. The negative feedback is still functioning. The fact the op-amp's output now needs to be a little more than a diode drop below the circuit's output will be no problem as long as we're using an op-amp with rail-to-rail outputs. Okay, I think we can take this back to the simulation. The new circuit performs just as well as the old one. The output voltage and current of the op-amp are a little bit asymmetric, as we expected, but the circuit output is right on the money. And if I cut the input voltage to 0, I have a trim pot that can adjust the quiescent current. I'm pretty satisfied that I can demo this circuit on the breadboard. The schematic and the Circuit.js models too are on the project GitHub as always. There should be a link somewhere nearby. About the only things that I haven't mentioned is their liberal sprinkling of bypass capacitors. And I've indicated my op-amp selection, an LMC6482, which is my current choice for an inexpensive CMOS op-amp with rail-to-rail inputs and outputs. My default JFET input op-amps are not going to be able to manage those voltage swings to less than a volt from the rails, particularly the negative rail. I've set up the circuit here on the breadboard. The LMC6482 op-amp is a surface mount part on a carrier board. The trim pot and servo transistor are right next to it. Then come the driver transistors and the output transistors. The ballast resistors are 1.3 ohm because I didn't have any 1.2 ohm ones on hand. That shouldn't make too much of a difference. I have multimeter leads monitoring the voltage drop across them. The quiescent voltage should be 65 millivolts if the quiescent current is 25 milliamps. I'll use a 10 ohm 5 watt resistor as the load. I don't have an 8 ohm dummy load on hand. This will probably limit the load current that we can push because the voltage drop of both ballast and load will be greater than I designed for. I'll begin with no voltage on the input and trim the quiescent voltage. I want to try to hit about 65 millivolts. And now I'll start running a signal through it. My first test is with just half a volt peak-to-peak, at the high audio frequency of 20 kHz. If you recall, those conditions are where our Class B amp had terrible crossover distortion, and that's why we went to Class AB. This amp is functioning correctly. I see no sign of the crossover distortion. Now I'll go to the other end of the audio spectrum, 20 Hz, which is where we get the most thermal stress on the parts. Peak and average currents don't change at lower frequencies, but the circuit is operating at peak power for a longer time. I'll increase the amplitude to the full 8 volts peak-to-peak. And I see it just barely starting to clip. I missed the calculation a tiny bit, probably because of the higher load resistance than 8 ohms. How am I doing thermally? Stuff is getting warm, but not horrible. The transistors are showing 55 or 56 Celsius. And even though my thermal camera is a cheap one and not all that well calibrated, my fingertips kind of agree. I can hold the transistors, and they feel toasty, but I don't have to jerk my hand back. They only go up a couple degrees more when I reduce the output voltage to the max of that parabolic curve. If I turn on my fan, the circulating air cools things rapidly into the low 40s. So now it's time to try it out on a speaker, right? Well, not so fast, Tiger. I haven't even started on reactive loads, and they will put significantly more stress on the amp. I'll pick up this thread next time by looking at what an actual speaker's impedance looks like. I hope you'll stay tuned for that, and maybe ask YouTube to remind you when that video comes out. In the meantime, stay safe, stay healthy, stay curious, and please take care of one another. Bye!